testing for many years. This, I definitely can assure you, this is also my first time to give a tech talk right from a street. That's entirely outdoor setting. You are lucky that Texas is not so hot these days, and in Cabans it's going to be too hot for that. So I'm sitting in this Cowboy Pavilion for most of the day, and I heard a lot talk about running LLMs with Kubernetes and in the cloud. And I have to say I'm very impressed because a lot of other speakers has conveyed why it's necessary to run your open source LLMs, fine-tuned LLMs, RAG, vector database, and all that stuff. And they have also talked about the challenges and the ways that you're going to orchestrate those very heavy workload in Kubernetes, right? My talk going to be a little different. So the title of my talk is Lightweight Large Language Model Inference with Wasm. Wasm meaning WebAssembly. So I see that most of you guys don't have your laptop with you today because you are here for for a conference that to hear the talks. But I want to assure you that I'm going to give you some very simple demo, and you're going to be able to memorize them in your mind. And by the time you go home, you'll be able to run a full-scale large language model, meaning like LLaMA 2.7b or LLaMA 2.13b, on your own laptop, like I do, or on a cloud server that you got from Azure or AWS. Right after this, by the end of the 40 minutes. Okay, so let's get started. Before we get into that demo, let's also talk about a little bit of the challenges of running large language models in the cloud. So I think it's boiled down to two problems. The first is, I think not a lot of people talk about that, is runtimes are super heavy. If you think about running a large language model using, say, the standard toolchain like PyTorch, did you realize that the PyTorch Docker image is almost 3 gigabytes? And if you have any other toolchain associated with, included in that Docker image, it goes to 7 gigabytes. That's just the image they publish on Docker Hub, right? So the base Docker image is very heavy. And the large language model itself is also a couple gigabytes, okay? So that means if you are running it in the largest data centers, it's probably okay. But if you want to run it on the edge, if you want to run it on robotics, if you run it on your own computer, it's going to be a very big challenge because it's the runtime is just so big with the standard toolchains. The second problem is a problem we really have not had since, I would say, 1996, since Java came along. I think everybody remembers the slogan of Java is write once, run anywhere, right? And so, it solved the problem of, I write an application on my laptop, but I want to deploy it on the server. How do I guarantee the same workload gonna behave the same on my machine and on my server? So the Java virtual machine come along to say that you can do that. It's gonna provide portability. The portability story goes on in the cloud native space, become containers. Container offers cross operating system portability, but it doesn't really offer CPU portability. So even in the container and Kubernetes space, you have a little work that you have to do to figure out whether the deploy machine is, say, ARM or x86, and choose different Docker images for that. But in general, it's fairly manageable. That's it's not a huge difference. Wait until you have AI workloads. You have large language model workloads. Now, the complexity really explodes. You not only have different CPUs to deal with, you have different GPUs to deal with. And within one GPU, you have different frameworks. So for instance, Nvidia GPU has different versions of CUDA. And if you want to get high performance out of it, you need TensorRT. Those are different software frameworks that running on the same hardware framework. And then you have NPUs, which is ARM's version of neural processing units, and Apple's version. They all have different SDKs. You have TPUs, and yesterday we saw there's LPUs, right? There's this company called Grok that's give you instantaneous large language model response within milliseconds. So they have a brand new hardware that is similar to the Google TPU, TensorFlow processing unit. And if you look at the large cloud providers from Microsoft to AWS, every single one of them now have their own chips to do AI inference, right? So we are now again have a explosion of hardwares and the drivers and things like that. And to use the container metaphor to address those problems is not going to be sufficient today, because each of those hardware and the software driver combination, you need a different container runtime. Just remember, your regular container runtime does not have access to the Nvidia GPU. Your Docker on your Mac does not have access to your GPU on your Mac. It only has this, access to the virtualized CPU. And you need specific container images. The container image has to contain, say, the CUDA toolkit or the Metal toolkit that is compiled specifically for the hardware. And you need different applications, different application code. So I think if I were to say, what's the biggest challenge of deploying LLMs on the in a way that is cloud native, I would say the biggest problem is the problem that we thought we have solved almost at least 20 years ago, 25 years ago, right? And it has come back with a vengeance, is that you can no longer assume that the application you write on your development machine is going to work on the production machine. In fact, there's a high probability it just wouldn't work, right? So I have two little problem scenarios that I think everybody can relate, right? So the first is that the developer created an LLM inference application using his laptop or her laptop on, say, Nvidia 4090. It's one of the gaming GPUs, right? Now he wants to deploy on the Nvidia A10G on AWS. Is that easy? It's all Nvidia, so it sounds easy, right? But in all likelihood, the deployment is gonna fail because it's gonna use different versions of CUDA. It's gonna use different versions of, it'd be a struggle to install PyTorch on both machines, even with Docker images, right? So it's not just I'm thinking that. Greg Brockman is the president of OpenAI, right? So he said much of the modern machine learning is making Python not to be a bottleneck. And that was just 2 days ago. That's the current status: installing dependencies, installing the correct toolchain on the development machine and on the production machine to make sure that they match, so that the application you write can run on the target that you specify, right? So I think about a year ago, somebody claimed AGI would be built in Python. Let that sink in. And the famous guy said, Rust. That's because I think they're coming to a consensus among people who really need to do large scale, cloud native scale inference on those frameworks, that Python is not going to save us. It's the same thing as when Java came along. People say there's Pro. I don't know if you guys remember. I remember that vividly. People say Pro scripting is cross-platform. Why do you need Java? It's the exact same argument. The scripting language is not going to save us from this mess, right? So this is problem one. The application developed on your machine cannot be guaranteed, or in all likelihood would not run on another machine that other people have or in the cloud, right? The problem number two is that, say if you don't use Python, so you don't have the problem with the 3 gigabytes runtime, that's you use something like the LLaMA CPP, right? It still has a portability problem because it's in a heterogeneous cloud. You have edge cloud, you have hybrid cloud, you have private cloud, you have public cloud. Each of those has a different machine. The entire cloud native toolchain is set up to orchestrate binaries. It is not to orchestrate source code and compile that binary on the target machine. We thought we have solved this problem a long time ago. So you cannot have a single set of artifacts that's being deployed across different machines and moved across different machines. So to say some of the workloads going to be running on this machine when this machine has more capacity, or running locally when I need more privacy. But but the same workload or the same setup would be migrated to AWS machine, when the condition changes, right? So you cannot do that because you have to recompile, retest, and redeploy on every single platform that you have. So that makes the deployment become a nightmare again, right? So the application framework I want to talk about is called LLaMA Edge. So I'm the creator of an open CNCF project called Wasm Edge. So we have what do we call the cloud native WebAssembly runtime. It is a WebAssembly runtime outside of the browser. And the moment I see large language model and the lack of portabilities they represent, I thought the Wasm virtual machine could do the same thing the Java virtual machine has done in 25 years ago, right? So how it works. It is an abstraction layer on top of all the hardware runtime and software runtime I talked about. So the hardware manufacturer, including Nvidia, Apple, ARM, and the software, AMD, Intel, and the software is TensorRT, LLaMA.cpp, MLX is Apple's latest framework, Metal, and things like that. So the work really is that because WebAssembly is a language agnostic runtime, so you can have several front-end languages. But Rust is probably the best supported. But JavaScript is closely there as well. We're going to have JavaScript support for large language model fairly soon. So basically, you write your application in Rust or in JavaScript maybe in a month. You compile that into Wasm, okay? And you don't need to worry about what's underneath Wasm. You don't need to worry about whether it's running on Apple or on Nvidia or anything else. Because for the developers, the abstraction stops at the Wasm layer. So you compile that to the Wasm bytecode. Then you ship your Wasm bytecode, okay? You ship it to your Kubernetes cluster. Or you copy it, do a file transfer to one of your friends, whatever you do. You can just ship it like a Docker image, right? And then on the ops side, the people who manage those host machines are responsible for installing the correct drivers. And so the system admin, so to speak, the correct drivers and Wasm Edge runtime that matches those drivers on those target machines. And when they receive the Wasm file, they would be able to immediately run it, right? So by doing that, we separate dev and ops again. So dev and ops used to be separate. Then it becomes a single word called DevOps. But I think with the portability becomes so complex, now it makes sense to have dev and ops separate again. So there's people whose responsibility are managing those machines and make sure the software on those machines matches the hardware. And then there's developers who would just write application to a common standard and then compile that common standard to Wasm and then be done with it, right? So I'm going to take maybe the next 15 minutes, which is majority of the talk, to do a demo. The demo is called Write Once, Run Anywhere, but for GPUs, okay? So it's no longer your previous generation of Java, but it's a new one, okay? So I'll come back and start a terminal here. So the whole thing is we have those one-liner script that that automate a lot of those installing processes. So I'll copy this and paste here. This is something that if you have a laptop right now, you can follow along. If it's Windows or Mac or anything, right? So if I run this script, what it does is that it's probably difficult to read, but this is essentially an overview of what it does. So to say, do you want to continue? Yes, I want to continue. So it's then now the first step. The first step is to install Wasm Edge. And if you already have Wasm Edge installed, you can skip it. Like me, I already have Wasm Edge installed, so I say keep my current version, right? Then it says, choose a large language model. So it gives you 12 language models to choose from. If you look at Hugging Face, the LLaMA 2 family of large language models, if you do a search, there's over 4,000 of them. So everyone has their own large language models. They are fine-tuned on different data sets. They have slightly different architecture and all that. So there's 12 here that we thought are mostly commonly used. However, if you want any of those at 4,000, you can enter the URL here. You can enter the Hugging Face URL. It's going to just go to Hugging Face and download that model for you, right? So in this particular case, I would just say I want the LLaMA 2 7B, which is I would say most standard. It's Meta, it used to be Facebook, right? So they have AI Lab that they release that, and a lot of the open source models are based on that. So and it's fine tuned for chat, meaning that it follows conversation. So I would just say 1, And because I have downloaded it, so it skips the download. If you haven't downloaded it, it's gonna go to Hugging Face to download that model for you. The model file for the 7B model file is about 4 gigabytes, right? For the 13B, it's gonna be twice as big, things like that. So now it gives you two choices. It can start an API server or a chatbot or a CLI chat. In order to make this demo more exciting, I'm gonna do the API server. So it's gonna start a server, okay? Download the server application. So the server application is a .wasm file. It's a file, I'm gonna show you in a minute. It's a file that's written in Rust and compiled to Wasm. This is the file that we talked about, right? It's a cross-platform, the file that can be orchestrated by Kubernetes and can be copied everywhere. Since I already have it, so I would say no, it doesn't. Don't download it. Now it gives me the command to run this application. The command basically is Wasm Edge, which is the WebAssembly runtime. It loads a large language model. It loads the Wasm file, and then gives a bunch of parameters in terms of how do we want to run this file, how do we want to run this model, right? So continue to start the server, yes. So what it does is that it now downloaded the Wasm application, downloaded the large language model, and it starts a web server on localhost. I want to demonstrate to you that this really is running locally on my Mac. This Mac is fairly old, and I don't have power plugged in, okay? So it is running in the lowest power configuration. I'm gonna turn off Wi-Fi, okay? So there'll be no, you see that? There's no Wi-Fi on this machine. So to make sure that the server and everything else is running locally, what I'm gonna do is that I'm gonna open this URL. So it runs the server and serve a static web page called the chatbot UI. Now I can ask it questions to say, where is the capital of, say we have a friend from Tokyo, so let's say Japan. The first question is a little slow because it needs to load the model, the 4 gigabytes model into the memory, and also because the whole thing, the JavaScript and front-end JavaScript and back-end server also all runs on the same machine. So it answers the capital of Japan is Tokyo, okay? Then let's ask a question, what about the USA? Sorry, the USA. You can see this is much faster, right? The capital of the United States of America is Washington, D.C. It's interesting that it follows the conversation, right? Because if I just ask a question without context, what about the USA? What about the USA, right? There's no answer to that question. However, because I asked what is the capital of Japan, and then ask the second question, it knows that I'm asking about the capital, right? So let's ask a harder question to say, is Houston the capital of Texas? Definitely the largest city. No, the capital of Texas is Austin, right? So this is right where we are. So, that's a very simple example to show you that the conversation can go on. You can ask it to, if you have a code, if you chose a model that's code LLaMA, you can have it write code, you can have it review code, you can do a lot of things. So the point of this demo really is that, it runs on reasonable speed. If you look at the log here, it runs on 26 tokens per second. For a human to talk, we are about 5 tokens per second, okay? If I talk, it's 5 tokens per second. If I talk really slow, it's about 1 token per second, something like that. So for 26 tokens per second, it's actually pretty fast. It doesn't feel that fast on the UI because everything is running on this machine. So there's a large JavaScript application that has to contact the localhost backend, which has to translate that into the large language model. So there's lots of threading, memory swapping going on here. But still, it's very acceptable. And if you have a newer Mac or Mac with larger memory, say if you have a Mac that has like 28 gigabytes memory, you can easily run the largest open source model that is out there. And so those models are much more capable than the 7B models, right? So what I'm trying to say is that there's go home and get your old Mac or get your Windows computer. Say if you have a Nvidia CUDA, it's the exact same process, to run the script and install Wasm Edge, download the file, download the model, and then you will be able to turn off your Wi-Fi and run it entire locally. So let me turn back on the Wi-Fi, okay? Because I want to and close this tab. What I want to show you is Control C out of it. What I want to show you now is I have the Wasm application downloaded on my Mac. Now I want to copy it to another machine in the cloud that's running Nvidia. And we all know the Nvidia instruction set and the Mac instruction set, especially at GPU, is drastically different. Can we do that? Can we run it without recompiling anything? So what I would show you is that because I set up ngrok on this. Sorry, let me go back to my presentation. Where's my presentation? Okay, here. All right. Oh, well, before we do that, let me show you the code. The code is actually really simple. So there's a GitHub URL. Everything here is open source. There's no secret. So it's if you are familiar with Rust, is that you can start a web server in Rust using the Hyper framework, and then you can specify the request handlers to say if HTTP request comes in, I want to pass the request to a function, right? To have the function handle it, and that's the handler function. So we design everything to be to be modular, so that you can set the prompt and then call the backend to do the inference. And the point I want to make is there's no Apple specific code here. There's no a code about the Metal framework or the MIX or anything that Apple provides. Everything is standard. What we call Wasm. It's a standard interface for WebAssembly, right? So you write this application, you compile it, and how to call the Metal framework underneath it is the WebAssembly runtime's job. It figures out how to do that. So the developer don't need to figure out how to do that. And because of that, it can cross-platform, goes to another GPU system. So let's do another GPU system. So what I'm going to show you is that I'm going to load this URL first, and it's going to say the server is not running. So I'm using an ngrok agent on the virtual machine that I have set up on Azure, right? So the virtual machine has a small NVIDIA GPU called T4. So it's one of the cheapest GPU machines. But since I don't have my server running there, it's going to say, it can find the agent, but can't find the service, right? So now what I'm going to do is I'm going to log into that machine. I SSH into that machine and cd demo and list what's in here. So there's two files in here. The large one, the one that's 4.7 gigabytes, is a LLaMA 2, is a model file itself. And then there's the UI files for the HTML pages and all that. So what you see missing is the application itself, right? The Wasm file is not here. So the Rust application, we compiled to Wasm, but that one I compiled it on my Mac. It's not on the Nvidia yet. So what we're gonna do is that from the Mac, we're gonna copy that to the Nvidia machine using SCP. So everything is just very simple, right? So you can see I put the private key here, and I specify the Wasm file name, and then Azure user, and then that's the directory is gonna just copy over the whole thing. And the file itself is only like 2 megabytes. So unlike a 5 gigabytes PyTorch Docker image, right? So here, if I do the list again, I'll see that I have a new file that is API server.wasm, and it's more than 2. It's 3 megabytes, right? So now with Wasm Edge installed and the model itself and the Wasm file, we can now start the server now. And let me find the command to start the server. So this is a command to start the server, which is exactly the same as the one we used for the Mac. So it tells Wasm Edge where to find the large language model and where to find the Wasm file, and on which socket to start the server. So I start the server. Huh? Why? Okay, let me. You know, some. So to do the demo is always difficult, I guess. Bytecode offset. Do I? Did it copy over the whole thing? Oh, it didn't. See, somehow it didn't do that. Let me try it again. So the SCP failed. It didn't copy over the entire file. Why? So now it works, right? Okay, let me see. Yeah. So as you'd expect, right? You know, if the file copying was interrupted in the middle by the terrible Wi-Fi here, you know, then you wouldn't be able to do that, right? So it started on localhost, and now we can see it. If we reload this page, because this page is we use ngrok to make the localhost available on the internet, right? So if I reload this page, it shows up the chat interface again. So if I ask it some other question, so let's say plan a 2-day trip to Austin. So Austin is an amazing city with plenty of things to do. Here's a suggested itinerary for 2-day trip to Austin. You can, it kind of goes on. It tells you to go to state capital, which is good. There's lots of things to see there. It says go to 6th Street for the live music, which is also good. And evening to Franklin Barbecue, although that is not correct, because Franklin Barbecue only opens in the morning. Yeah, so you may have to hire someone to stand in the line for you to get the barbecue, but you get the idea. This is a 7B model. This is not it is not a crazy smart model, but it can spill out so much information about it, and it's reasonably fast, right? So if you look at those. On this Nvidia machine, it's actually faster than the Mac that I have. It's 37 tokens per second. It's actually the inference has finished long ago. It's just the JavaScript is still streaming it, right? So now we have this on the internet. We can do something that I thought it'd be even more interesting, is that because this is called an API server, not for no reason. It does have a web interface, but it also has a you can use the OpenAI style queries to run the to interact with it, right? So here you can see I have a curl command. I post to this URL that we talked about, and here from the V1, the rest of the URL is structured very much like the OpenAI API endpoints, right? Except you don't need to pay because that's your own machine. And you can set up security and all that, if you want to. And the message, with those large language, because those large language models are essentially stateless, so every time you have to replay the whole conversation for it, right? So the messages, there's a role to tell, you are a helpful, respectful, honest assistant. Always answer as short as possible. See, this is one of the prompts that to say, answer short, right? And then say, where is the capital of Texas? And it's going to come back instantly. It says the capital of Texas is Austin, right? It answers as short as possible. In fact, I want to try, if I don't have answer as short as possible, would it give me a longer answer? Let me see. Here. Let's also say, where's the capital of Texas? Yeah, it gives me a longer answer. Of course, the capital of Texas is Austin, and have that smiley, Did you know that Austin is known for vibrant music scene with, a large variety, whatever, right? That's, so it's, yeah, so, there's a lot of fun you can play with it, So we have an engineering office in Taipei, and I bought Nvidia Jetson device, which is it's about this big. It has a Nvidia GPU in it with 64 gigabytes of memory. So we run the code LLaMA in there for the purpose of being our own coding copilot. So we don't use the GitHub copilot for it. We use the code LLaMA to review our code and to identify errors. That's you'd be amazed. There's a lot of things that it can identify. You can also prompt it to say, when you review this code, make sure that every function has a unit test. It will tell you which one doesn't have unit test, and things like that. So it's a tremendously useful by having an API like that, because then you can connect with the other tools that we've seen throughout today. Say Flowwise, LangChain, LLaMA Index. They all work with this style of APIs, right? So you can have those things stand up on the on your cloud server with very little effort. So, this demo is about, I spent a little longer, that's 17 minutes on this demo. So I've showed you both running on locally on my Mac and on a cloud server with the Nvidia GPU. You should be able to do that within 10 minutes when you go home as well. So that's, well, I have a couple more minutes. So here's the API server. And there's another GitHub repository that we have to say, people say, okay, what you have shown is a toy. That's because you run a single-threaded server. It's like a Node.js server. That's how about I want the scalability? I want to run it on large GPUs or machines with multiple GPUs. So we have a little repository with script and configurations to run this with Nginx, right? So essentially you have different workers. Each worker is a Wasm Edge instance, and then you have Nginx sitting in front of it, and to connect to the least connected worker. So there are some performance metrics that you can see as well. And as you can see, the Nvidia 4090, which is a consumer grade GPU, it's actually really, really fast. It's about several times faster than, say, the Nvidia T4 that we just saw, right? So there's lots of interesting things that you can see. But so here's a GitHub repository that you can go and set up yourself once you get Wasm Edge running. So then perhaps close to the final point is that I want to talk about how you want to build LLM agent and applications, because I've just shown that you can run the LLM agent in your own application, but see the model in your application. But how do you want to build a copilot? Or you want to build autonomous driving, you want to put it in a car or in a bot, something like that, right? So option one is really to use the API server we just shown, because the API is compatible with OpenAI. So there's a large variety of tools that can work with it. And so the benefit of our is, obviously there are other API servers out there, because we are definitely not the only one doing that, right? That's so our benefit really is that it's very light. There's no Python dependency, and it supports a great variety of hardware and software accelerators that I've just shown, right? And however, the problem is also because you have to build your application logic outside of the API server. So at the application layer, you still have Python dependency, because LangChain is based in Python, and the LLaMA index is based in Python as well. So another way to do it, which I think is the more optimized way to do it for applications that you need to squeeze out more performance to be smaller and to be faster and to truly run on the edge, is to use LLaMA Edge as Lego blocks. So we provide a set of components in Rust, and soon will be in JavaScript as well. So where you can assemble your own application without interacting with the APIs, because the API has to go through the network and then come back, right? But you can have direct function calls in memory to interact with those large language models. That allows you to do a lot of things. So for instance, you can do the RAG applications without a lot of frameworks that are around it. You can do advanced API services. If you look at this field is going so fast that the OpenAI API itself is changing all the time. They have function calls, they have assistants. Every couple months they have a new API. So to keep up with those innovations, you need to you need to do this in your own API server as well. So there are lots of things you can do. You can also do multiple models, which is the great thing about open source models, because you can choose different models for different tasks. They are all they are fine-tuned for different purposes, right? So I think my time is always up. It's almost up. So I want to leave some time for Q&A. But the one last thing I want to say is that we started the journey of GPU agnostic AI inference with WebAssembly long before LLM come along. So we actually have a lot more other models. Not just the LLaMA models. We have those models, like PyTorch, we have, TensorFlow, we have OpenWine, we have YOLO, we have all those things. And so there are some documentation and examples, like image detection and, object detection, images and, stuff like that. And from our GitHub repository. And if you are interested, you should go there and have a look, So yeah, that's, let's have 2 questions,
So in order to install the model, is it like we can install on some sort of EC2 machine using the GPU, or how does it work?
Yeah, so it works on GPU and CPU, right? So essentially, the process I'm showing works on any EC2 machine. So on EC2 machine, you run the script, it would ask you to install Wasm Edge first. And then it says which model you want to download. You download a model, right? If the machine only have CPU, it's going to use the CPU to do inference. The effect is you're going to see it fairly slow. You're going to see it's like a person speaking very, very slowly. That's the capital of Texas is Austin. Something like that, right? But if the machine has GPU, it automatically uses the GPU. So I think that's a strength of it. It achieves cross-platform not at the lowest common denominator, but at the highest performance it can get, right? So yeah. So go home and see it. Try it.
Do you have plans? Oh, actually, thank you. Do you have plans to make adapters to make this run on Wasm Edge platforms like Cloudflare Edge or anything like that?
And
so do you know how there are already like Wasm targets that you can deploy to? So Cloudflare Edge is one of them. There are some other products. Do you have plans to make like adapters to make that deployment easier?
We would really love to have cloud providers using us as as a runtime, right? By the way, Civo Cloud, they have just announced their Edge product. So Wasm Edge is one of the options, right? So the idea really is that to go through the standardization process. It's called WASI neural network, and it's a W3C standard. So it's one of the it's because everything's so new, so it's still going through that process, right? So once it's being standardized, my expectation is that most of the what I would call serious Wasm runtimes would implement that. So we would compete on the quality of runtime, not on who has the APIs that other people don't support, right? But that's as you know, the open source standardization effort takes a very long time. If you look at Java, the JCP process, that was it used to be, we hope we can do better this time, right? So. Oh. Thank you. Yeah.